My name is Pierre Olsson. I work at Strusoft as a team leader for application for structural design. My background is probably similar to a lot of you guys. I went to LTH, Väg och Vatten in 1994. So I'm a B94 to begin with. So my background is primarily in structural mechanics, that kind of stuff. I did my PhD at Chalmers, like a cross-disciplinary thing between architecture and structural design. And then I started to work at Strusoft, and I've been there for 13 years now, more or less. So I thought I should start by introducing the company, Strusoft, what we do, and how we do it. And I will start talk a little bit about mainly desktop applications. And then my colleague will talk a little about web applications. Right. So let's start. Strusoft was originally a part of Skanska and was made into a standalone company in 2002. So basically what we provide is specialized software in terms of structural design and analysis, basically all kind of tools pertaining to the building industry, that being both in terms of structural design of in situ buildings and also in prefabricated elements, energy, and a lot of other stuff related to the building industry. We have offices in Sweden, Denmark, UK, Estonia, Hungary, Philippines, and India. We have a few big software suites, and I think I will mention the ones that are most likely to be interesting for you guys, I think. So let's start with Winstatic. Winstatic are more or less quite specialized, small, simple desktop applications pertaining to structural design, mainly concrete. So what we see here is like the startup menu for Winstatic. And when you see here, we have small and simple programs for doing concrete beam calculation, concrete columns, just plain sections and punching, and also a little bit bigger models in terms of trusses and frames, and also some special tools for masonry design, for example, and also pre-stress, which is one of the bigger ones, which basically analyzes pre-stressed structures such as hollow cores and similar. And we also have geotechnical programs in terms of foundation, retaining wall, and settlements. So I think I should just show you concrete beam, for example. This is a very simple program. Basically, you start, let's say, let us do a simple beam. Okay, there's one span, maybe it's 5 meters, something like that. We have maybe some material. We see what kind of concrete strength we have. All right, let's do that. We put some load, maybe some uniform load on that. 2 newtons per meters. Add. Okay. Calculate, and we're done. So this is the analysis parts, and then we have the design part, which basically adds reinforcement to the beam. So this is like a very, very particular thing that the structural engineer out there will be doing more or less on a daily basis. So here you get what kind of reinforcement is required, both the longitudinal reinforcement and also the vertical. And that's basically it. You do a report on this, and then you're done. And this is basically what all the programs look like, and what kind of scope they have. in terms of the WinStatic programs. Right. So let's have a look at another product in terms of structural design. It's called FemDesign. The text is very small. I don't expect you to read it. Basically, it is the same thing as the WinStatic, but it's on a bigger scale. It is the entire model. It can import models from Revit, from Tekla, from AutoCAD, and you can do a solid modeling of the entire building. So this is basically used quite often for calculating the design forces. So you have forces from wind, snow, and all sort of freeload that will be calculated down through the building, and it will affect the different elements down through the building. And then you can take that particular element and you can do a more detailed study in FemDesign, or you can do it in WinStatic actually. So let me just show you what it looks like. So what we see here is actually FemDesign in action with the same model that you have there in the slide. So this is what it looked like. I just wanted to give you a chance to see what it actually looks like. So there's a lot of options. It looks like an AutoCAD. And you can then define your different elements. You can put loads on there. You can put boundary conditions. And you can get all sorts of nice results from it, and also do a design, meaning adding reinforcement to the concrete elements. Right. So that's what FemDesign. The next big thing we have is Impact, which is basically something different. It doesn't really do any calculations. This is more of a what you could call it, like a design and planning tool. It is a plugin to AutoCAD or Revit, in which you actually design your structures, your beams, your walls, your floors. You put all the details in it. It's like a BIM tool, basically. So what you see here in Impact Design, this is where you're in AutoCAD or you're in Revit. You're actually drawing and creating the building elements there. And you do it with special tools and special macros that actually saves the data you give into a database. And from the database, you can, of course, create your model again, or you can say, okay, give me the drawings that it will be required to do these elements. And also, you can use it for planning. For example, you see the impact production tool, which is basically something where you actually plan. Okay, this element needs to be constructed first. So we plan that one. We put that in the forms first, and then we cast it. We do it in a particular order. You say this one is done. You can tag the different ones being finished, and when they are to be moved out from the factory floor to the back lot, and when they're to be planned on the lorry, actually, which element should be placed in the lorry and where, and taken out to the site, and which actually is added into place. So this is a whole of designing and production planning a bit. And this kind of tool is something that we work with big companies that do prefabricated concrete elements, such as strängbetong, A-betong, Starka in Sweden and the northern countries, basically. So let me just show you a little bit of what it could look like. It could look like this. What we are looking at now is a building that has been designed in project manager. This is this. You actually can see the building. You see it's been built with prefabricated element. It doesn't really look really finished yet, but this is the backbone of the building. And here you can get an overview of what this building entails, what's in the different floors and whatnot. And even though it doesn't do any calculations, per se. We have connected it to another one of our programs, Pre-Stress, which I mentioned before. So you can actually, from this impact program, you can open in like in a calculation view. And you see this is like one of the floors, and these are floor elements, hollow cores in this case. And you can select one, and we have made a quick connection to the calculation program. We start the calculation, and what you see now is data being connected from the database I mentioned. It is being comprised into a data file that is being sent into the calculation program, which is this case in Pre-Stress, which is now is running in the background and doing a code check, which is more or less the strength of the WinStatic program. Not just the analysis, but actually doing the code check. So now it's actually looking into Eurocode and see what kind of demands there are, and try to figure out, is this do we have enough reinforcement? Is the concrete strong enough? Will it take all the different loadings and the different load combinations according to code that it's required to take? And in the end, we will get some sort of report with all the nitty-gritty details, and we'll also get some sort of indication here in this model view, where if the checks were good or bad, basically. So let's see, it's still running Pre-Stress in the background. We see here. Let's see if we managed to finish here. It takes a little bit of a while there to get it up and running, but I think it's calculating now. Yes, it is. So, well, either way, there will be a report. Oh, there we have it. It's very small. I don't think you can see what it actually says, but it basically has the most important things required for a calculation report to be sent to maybe the instance in what country it is used. Sometimes it's been sent to the authorities for them to sign off on it. So it needs to produce some sort of report. And here we would also have seen if it was good or bad. So what we see here is like a green light. Okay, it passed all the checks, so it's fine. Right. Okay. So let's go back to the presentation here. Basically, what I mentioned now is the applications for structures that we do at Strusoft. So that was what we do, and I thought you should talk a little bit about what we do, because I wanted to give you a picture of what it's like working with system development in this respect. So let me just mention a little bit what kind of tools and methods we use, and maybe you can get a picture of what we do on a daily basis. So most of these projects, if they are projects, or if it's just an addition to a new program, or if it's a completely new program, it starts with the technical specifications. Now, Strusoft has basically two different kind of developers. There are the developer with a strict system development background, which does know everything about frameworks and all the specific programmings and all the build tools and whatnot. And then we have the engineers part that's are proficient in structural dynamics and structural design and analysis. And we have those that are a little bit in between, like myself, which has a background in as an engineer, but also do development. So the whole thing starts with the technical specifications, which is basically, this is the different steps the program needs to do. You need to calculate according to this. These are the formulas. And then this has been handing over to me, basically in this case, as the team leader. And then I will create tasks, basically. And that I do in some helper tools. We use Trello, for example, and also Fogbugs, where we can divide a big project into more manageable cases. And then we plan them. In Scrum meetings, we do like different sprints. I think we have mostly 2-week sprints. We plan what we should do within a 2-week basis. And we say, okay, this or this or this should be included in this latest sprint. And then we assign each step to different developers. Then they have their task to do, and they have the description of what it entails in Trello or in Fogbugs, which are tools. It could be any kind of tool. It's basically just a way of handling a task. For the desktop applications, we have kind of a wide spectrum of everything from C to C++, C#, to Fortran actually, and also a little bit of Delphi. It's mainly, you saw Impact there before, which I showed you. That's C#. That's a big C# product. And WinStatic is basically C++ in the bottom. And then we try to, it's a little bit aged, as you probably noticed by the UI design, but it still works pretty good actually. So we use Microsoft Foundation classes and also Qt for user interface design mainly. Development tools that we use, Visual Studio, basically, especially for the ones that's using C#, there's a lot of special tools there for the .NET development. So they use Visual Studio, or we use VS Code, which is more or less the same, but it's free. It doesn't really have all the bells and whistles. And for managing the source code, we use Git, which is more or less a branch standard, I would say, where you can have your you can branch off and you can test your ideas, and then you can merge into like the main working line for the program. And also you can go back and forth, and you can merge changes into a main folder. We also need some sort of tool that actually builds our code on a daily basis. So we have that distributed in the cloud. We use something called TeamCity. I know there's a lot of other tools. Basically, it takes care. It pulls all our source code, and it builds all of our applications, and then they install it on a test machine, and it runs tests for us. So that's regression tests. So that's an automatic process that we don't have to do manually. We just say that after we made a big change in the source code, do a rebuild. And if we need something in between, maybe we do some install script, we do some scripting, and that's basically mostly Python or NSys. So this gives a little bit of a picture of what we do on a daily basis in terms of desktop applications. So I think that's basically all I wanted to mention. So I think I'm gonna leave it to Andreas, and maybe we can come back for some questions at the end. All right.
Thank you. Great. Yeah. Hello, everyone. Thank you, Pierre, for a great introduction and the presentation of all your stuff. So I will take over the screen to begin with. All right. Okay, so my name is Andreas Rudenå. I have a typical software engineer background, software developer. So I have not too much background in the building calculations, stuff like that. So I have worked at Strusoft for almost 10 years now, with mainly web development and cloud development. So this is what I'm going to talk about now, actually, because it complements a little bit the things that Pierre talked about. So first, I want to introduce you to some of the software that Pierre didn't talk about yet. I have opened the web page here, Strusoft.com. This is another desktop software that we have worked on for many years. So it's energy simulation. Now this is in Swedish. So, but anyway, I will explain what it does. So this desktop software was started to be developed, I think, at least in the 80s. So it's a really, like, it has an old history, and it's an energy simulation software for building energy use. Let me see if I can. Yeah. Yeah, it basically handles the a dynamic energy simulation hour by hour for a building, and basically simulates then how much heating and cooling demand that exists in this building, together with a lot of other very detailed data that has to do with all the inputs and outputs that we can get out from this kind of simulation. And of course, it depends on the climate, what kind of materials you have in the walls and so on, how many people are in the building, and what kind of ventilation system you have, or if you have some heat pump or other heating system and so on. And this is an example on a weekly result over the year. So for example, a lot of solar energy is coming into the building during the summer period. Yes, some examples here from the charts. So if I take it from the beginning, when I started at Strusoft, I started to work on this energy simulation software with a specific task, and that was to actually create a new generation of this simulation that was run in the cloud. So if I go back now to the other, this one. And this is really interesting to start with how we work with these kind of calculations and simulation software at Strusoft, because it's rather complex and complicated sometimes, these kind of tools, and it has been developed for a long time in a lot of cases. And also being used in the industry for a long time. So one of the big kind of technical problems there is with this desktop software is that when you build software for back in the days, it was not as how do you say, it was not as modular as it is nowadays. So a lot of things happen during the years when it comes to develop software more and more efficiently. So this means that it's a challenge actually to maintain and to develop these old softwares for kind of to future-proof them. And of course, it's perfectly fine to in the future also to just install a desktop software and run the calculations on your computer. So this, I don't think this will change. But as we have seen some trends, and I think this is also very interesting to discuss and bring up. So that's why I will talk a bit about it. Is that we have the possibility actually to take the simulation or the calculation part from the software and run it in the cloud. Obviously, in a pure technical sense, you have to separate the user interface from the calculation. And this is one of the most tricky part with old software, because you didn't really do that kind of distinction when you developed in the old style. So it's more like the user interface mainly directly manipulates the inputs and so on. So this kind of extraction or way of separating the user interface and the simulation. So the simulation was extracted into a simulation core. This was done with the VIP Energy tool that I was talking about, and so the core was deployed in a cloud environment, and we started to develop then a web-based interface. So actually, what we are looking at now, finally, this is an example slide of this new product, and it's called BIM Energy instead of VIP Energy. So basically, what it is, it's a new web-based interface to this simulation engine, where we try to make the user interface a little bit easier to understand and a little bit more modern. So in general, this is very interesting task for us at Strusoft to create these kind of cores and develop new interface user interfaces for them. And what we're seeing now is on the web page some display of kind of what materials we have in the walls, and we have a 3D model of the building. I can select another slide here. We have some map functionality and some kind of drawing functionality, so that you can redesign your building. So this will actually change the geometry of the building. Here are some other examples of the simulation results. Actually, what I can do is that I can go over here to the real application and just give you a quick idea. English. Okay, so this is how it looks now with this new web interface. We have a workflow up here in the menu, where you can go through all the steps that's needed to do all the input, everything from designing the geometry to decide what kind of materials you have, to give some input around how the building is used with schedules, and determine some settings in the ventilation and some heating system settings and cooling system settings, and then get to the reports. So it's a new kind of more modern interface to the same problem, really, for doing the energy simulations. So I think I could talk for a long time about this tool, but I think I would like to more touch upon in general what I'm working on and the different kind of areas and projects. And then I really hope that if you want to know something more, you can just bring it up in the question section afterwards. So I will actually just move on a little bit, I think, because so far what I really wanted to mention is really I think the general demand for the building industry to keep updating the software technology, because it's also needed in the building industry. It's general kind of a slow emerging industry where things, it doesn't really evolve, how to say, grow as fast as in comparison to other tech industries, because people are more likely to work in the same way as they usually work. It's stable and reliable to do that, so they don't change the way. And it's important for us as software developers, because we cannot just start to work on the latest technology and expect all our users and customers to just switch to this technology immediately. I think many people like to stay in the same kind of tools and in the same kind of workflows, and it will of course change, but it changed a little bit slowly. So this is this is basically one important part of this evolution that we're doing on now to bring some things up in the cloud and to bring some new interfaces and see where we get, if we get a lot of more interest on this, or if people still want to, in this case, stay in the VIP Energy desktop, or if they want to go over to this Vim Energy version of it. So I will go to another slide here, and I will talk a little bit in general about technology, I think, because this is it's really interesting in this industry that we are working in, because I think the technology, the modern technology and the hype technology is really needed in the building industry. So it's like it has really two ends, this thing. We have a big need for digitalization and new technologies. On the other hand, the building industry is moving more slowly than, for example, the gaming industry or some other tech industries. And these are some topics that are relevant for me in my daily work. So I just wanted to go through them. So I think it's a very inspiring list. And this is to say that working with software in this industry is very, very interesting and stimulating. So what I talked about already is the energy stuff that I'm working on, and this is both with renewable energy technology, especially in some projects that we have been working on, and the energy efficiency is just what I talked about, the simulation for energy efficiency, and these are not really the same thing, even though they are related. Renewable energy is a super hot topic, and it has specifically to do with the transition from the fossil fuel and stuff like that to solar and wind and stuff, which is very important, of course, for the future. Then, as of lately, these things has become a lot more, how do you say, especially in the research projects area, gaining a lot of more traction and interest. So I'm working now with a very interesting project, and I should say that also before I used to work in the energy division of Strusoft, and now I'm working in another division called the Research and Development. So I'm working mostly with some projects that kind of benefits our other products in the long run. So I hope you know. Otherwise, you can ask me or Google about this concept with the more kind of the sustainable cycles, life cycle, and how to be more sustainable in general. And these things come in more and more in our software. So Pierre talked about Impact, for example, and they have recently released one life cycle analysis module because of the concrete elements. They want to use these kind of calculations in this industry as well, because it's important actually. And previously they didn't care too much about the carbon footprint and stuff from the concrete elements, but now it's more and more important. Digitalization in general is very important when it comes to existing infrastructure and stuff like that, to bring this into the system and retrofit and renovate and stuff like that, especially buildings. Digital twin is a super hot concept, and we started just a big project. It's more like a competence center that Chalmers is hosting, called Digital Twin Cities. So this is super interesting. In that case, it's a digital twin city, but digital twin is a very interesting concept also for the software industry and also the building industry or the manufacturing industry, for example. It's basically to replicate the real world with its all processes and everything into a digital environment, and enable simulations and kind of real-time visualizations from real processes and workflows in the real environment. So, for example, in a factory, you can model the whole factory and all those processes, so you can actually keep a virtual copy of this and do some improvements. The concept has been around for a long time, but this doing it with a city is it's pretty new and a pretty hot topic. Industry 4.0 is also very important concept for us nowadays, which is like the next generation of industry, and it has a lot to do with sensors and the real-time visualization of the processes and machines and everything. And it goes also along with buildings, for example, and it comes here with smart buildings, for example, to monitor buildings and control buildings in a really, like, you call it smart here. And this is also really interesting discussion, what is smart? But most often it's like sensors and control systems that are integrated in a way that it can help us understanding and controlling this buildings and cities. Building information modeling is, of course, it's read here. It's like one of the main things we are working on now. It's the information model of the building. In a pure technical sense, it has a lot of interesting challenges. How you represent the building in 3D and how you can do calculations with this model and how to keep it intact between all the phases in the building process. So if you're doing in the early stage, how you bring it on to the construction phase and how you bring it on to the maintenance phase and so on. So this is a huge topic and very interesting topic for the software development. GIS is also very important for us now, like the geographical stuff, but it's not so prevalent now in our software, but it will be in some of it later. Internet of Things and big data, cloud computing, machine learning, very interesting topic as well. And yes, we are working on those. I can show you some prototypes of some of the new things that are not released yet in BIM Energy, where we actually use the map technology and visualization and sensors and the kind of look into a little bit of this and that. And it's still very new, and we have a lot of interests from outside, but it's still a little bit too new for us to make a clear product from it. So we are looking into it a little bit on who are the customers for these kind of things and what part of it they really want. All right, I think that was it. I have a lot of things to say about all these areas, so I think we are. It's better just to open up some Q&A, I think, because I can talk a lot about everything here, and I think Pierre also can do it from his side of point of view there. So thank you a lot.
Okay, thank you very much for really nice presentations here. Is there anyone want to ask some questions here to Strusoft?
Everything was crystal clear and super interesting.
Yeah. Anyone?
I can ask how, but I don't know if Pierre told me maybe, but how the students are you doing software development or not, or do you have some courses with it, or is it mixed, or?
There are introductory courses in programming.
All right.
So this is a continuation course in structural mechanics, for basically how you construct the complete code from the user interface analysis code and visualization. And they currently work in Python and PyQt to do. Let's see, I have a question here, perhaps. Okay, we have a question here. I wonder, since we're using Python, what do you think about Python for programs as you may, in your context?
I would say Python is one of the most common programming languages in this field. I don't think we at Strusoft use this too much. We use it sometime, but we can of course see a big increase in Python. I think it has gone up to the most popular programming language now, especially talking about the machine learning and AI and things like that, and for a lot of calculations, but it's because it's kind of easier than C++, and it migrates good together. But on the other hand, going for web interfaces, it might be still a challenge, but of course that's not necessary for all applications.
And there are some large web frameworks in Python as well that you can use as backend. So yes. I have some question about the web. So how do you run it in the cloud? Do you have separated the computational backend from the web-based front end, or how is the architecture when running your applications in the cloud? What
yes. Yeah. Yes, so that's different from each case, but in general, it's very important that the calculation part is running separately, and by that I mean that it has a separate machine, and even that these machines can scale up, so you can run 1 or 10 of these calculations. So that puts a interesting demand on the applications system structure, because you have to kind of be able to proxy the request for calculation through something, and in the most simple case we're using just like a web server that can call these calculations, and it's a little bit tricky, but we are using Amazon Web Services. I mean, we are using Azure as well. Maybe you know the big cloud platforms like Google and Azure and Amazon. But I'm working mostly with Amazon, and Amazon has a lot of kind of services to help with scaling up this kind of system architecture. So that's what we are using a lot to kind of auto scale machines. If we see a big activity on the machine, then it can start up a new one and so offload. And I think this is very important. This is the most important thing. And then, of course, talking about web applications, we kind of still only have one main language to create a front end, and that is JavaScript. So I would say that most of the projects we are working with JavaScript on both the front end and the app and the back end, where the back end then connects the calculation core, which could be written in C++, for example. But the JavaScript in both the front end and the back end can make it easy to reuse the code base, because you can run the code in both the front end and back end, and you can choose. So sometimes we can even run simple calculations in the front end. So this is one of the benefits of JavaScript.
Another question I have. So when you're running in the cloud, the data that the users store. So the users probably paying for an account to log in, and they use their things in the cloud. So do you handle the storage of the data as well?
Yes, the storage of the data. We have the input data, like the project data, and this is and we have the result, the output from the calculations, and that's also a little bit depending on the application. But normally we store all the inputs, of course, and then and the output is coming back when you click a button or something like that. But we can of course also store the results. But I would say that the database stuff is where it's really beneficial to use the cloud infrastructure. So in all cases, in all production cases, we are using the in my case, the Amazon services for that, for the databases. So it's like a different kind of database. It's called RDS. Yeah,
and then you get redundancy and security as well when you have using their services.
Yes, yes, yes. We are actually using another service that on top of Amazon that is doing backups and like have some simplified user interface. So it's really convenient. And if it's one thing you really want to leave away to some other, that's the database, because that's the kind of the most critical and most cumbersome things to keep in track of, even to scale it and backups and stuff like that. It's a very critical piece. So yeah, just leave it to the cloud service. Even if it's more costly, it's really worth it.
Okay, so now I have two other questions here. I have one question here. Do you have Skanska as a customer now?
Oh, yes.
Is Skanska using other programs?
No, Skanska is a very big customer of ours. Of course, both for, I think they had a lot of divisions for prefabricated concrete, for example, but I think they've sold them off now. So I think what they have is like Skanska Technique, which is basically the design part. So they have a lot of Winsatic program, actually, also FemDesign, and of course Impact. Impact was actually co-created by Skanska. So they have had a big input on that particular program. Oh, yes.
Okay, final one here, I think. So I have also a question. What do you think is your edge compared to other competitors with similar software?
Well, we were first, basically. I think in terms of the Nordic countries, there's not that many competitors, actually. But in general, I think if you just compare it with any other analysis tool, it's the fact that we have the design part. We have the connection to Eurocode. So it's not just getting your section forces. You actually get, okay, this will be okay according to code, because as a structural engineer, if you come and you have these really nice diagrams of moments and shear forces, then I say, oh yeah, sure, that's very fine, but I need to actually have something that said this is okay according to code. So I think that's the main thing for the calculation program of ours, I'd say.
Yeah, thank you very much. Any final questions now? Yeah. Okay, another question here. So how big is Strusoft? How many employees and which cities are you mainly located?
I think we are somewhere over 100 employees at the moment. I think it's somewhere around that. The main cities we are located in would be Malmö, first and foremost, actually. We have 2 offices in Malmö. And after that, I would say the Denmark office, actually. We have a small office in Gothenburg and Stockholm as well, and in some other countries as well. But
yeah, also to mention the Budapest office.
Budapest office
is pretty big.
Yeah. The FemDesign is developed completely in Budapest, actually. So yeah.
Okay. So I'm giving a lecture in 10 minutes now here as well. So I will thank you very much for a really nice presentation and a good overview of your company and what you're doing. Also, part of how you develop software. That's also interesting to kind of for students to learn about. So thank you very much. And perhaps we will see some of the students at your place sometime. So
absolutely, we hope so. Yeah, that's great. Thank you for having us.
Thank you very much. Yeah.
Okay.
You're welcome to stay if you want. So, but I'm going to have a short break now. So, but you're welcome to stay along if you want to as well.
All right. If there's any question, that's fine. But you saw my email address there, so just send it to me if you have any questions. That's quite all right.
Okay. Thank you.
Okay. Thanks. Okay. Bye-bye.
Bye. So we will have a 10 minutes break And after that, I will give a lecture on some ideas on how you can think about user interfaces for finite element analysis programs in the future. So a short 10-minute break. We're back in at 14:15. Okay, thank you. Okay, so let's start again. I'm just going to share my screen here. So today I'm going to talk a little bit about user interface concepts on exploring forms and structures. This has been ongoing work at, for me, at Structural Mechanics, at least, to kind of look at different concepts in user interfaces for finite element analysis and also for exploring forms and structures. So how does computational tools how are they used in architecture and engineering? So the classical simulation cycle is that you should define a geometry, you add forces and boundary conditions, you define your materials, you run your simulation, evaluate results, and it starts over again until you find the kind of your design is correct and it fulfills your criteria. So it's quite iterative, but it's very step by step. And some of these steps can take longer than other steps also to execute. A typical example here is from a finite element called HACON, so stands for hardening concrete. It was originally developed by Ola Dahlblom at the department, and it was given a user interface by me and together with a consultancy company. So the idea here is you first create your model here, the geometry of the model. So in this case, you have let's see here if I can annotate here. You have your concrete slab here in this section here, and it's two-dimensional, but it's kind of stretches out in the screen. It's connected on the ground here with some ground elements, and it basically gives you a geometry here. Next, you define your materials on these geometry areas. So in this case, I have concrete on the top, and I have some ground materials that defines where the concrete connects to the ground. I assign my boundary conditions. In this case here, it's 10 degrees around this concrete when it's going to be cast. And then you calculate here. So now you do some time stepping here. So this is this program simulates the process of casting in time steps, and this can take some time to execute. So now you, as a user, you can't use your application. You have to wait until the calculation is done. Then you have your results. You can view your results here. You look at the temperature development, and then. But if I want to kind of change my geometry, I have to start from the beginning again and recalculate everything. Do the time stepping again. Wait for results. So there is no feedback between the modeling part and the visualization of the results of your calculations. So the discrete computation step interferes with the design process, especially if you have large calculations. And it's also kind of hard to when you're discussing a problem with a client or colleague, that you have to wait for the calculation to finish first. So it's also difficult to understand what happens if I change something. I have to wait until the end, and then I kind of forgot what I changed. So is there a solution to this? Can we remove this discrete calculation step? Can we make it kind of transparent for the user and do it in a different way? So one idea is to kind of have two windows open all the time. So when you change something, it automatically calculates in the background and shows you the results. It gives you kind of instant feedback, better understanding, and also encourage you to kind of explore changes in your model more intuitively. Of course, this has some other problems that, especially if you have a complicated model, it can take some time to do this. So how do we accomplish this? So first, little bit about computer theory here. So you have a usual model of a computer is that you have a computer with a single CPU processor. So it can do one task per processor. So a task can kind of be executed on this processor, and you have to wait until it's finished to kind of continue. Today you have this situation instead. You have a processor in your computer has several smaller CPUs inside, or called cores. And those can do multiple tasks per processor. So now you can all of a sudden do 4 really parallel tasks at the same time. So if you look at the classical modeling we have seen before, is that you model, you do computation, and you do visualization. You have these 3 steps that follow each other. But what if you introduce a concurrent model instead? So then we can do less with more. So you can model and do visualization at the same time. So every time, for example, you change a geometry in your model, or change geometry of your model, the program can be intelligent enough to okay, now I need to update my simulation. So I launch a simulation in the background on multiple threads. So kind of pre-compute before the user even knows that he needs or he or she needs a new calculation. And the visualization can be updated directly as well. And depending on your computer, you can kind of add more and more cores to your simulation. So if you have 8 cores, 16 cores, the simulation gets even faster. And if you look at some of the trends we have today, the clock frequencies of computers, you probably have noticed that they are kind of not moving about 3 gigahertz, something like 3.5, but it has kind of stopped because energy to kind of drive this processor is so high. It's really hard to kind of get performance of that. So what people, or what the companies that manufacture processors did was kind of, instead of increasing the clock frequency, they added more cores. So today, for example, on our big computers that we manage at Lunar, for example, every server has at least 20 cores. So there are 2 processors with 10 cores each. And all of these can, so that machine can actually do 20 tasks at the same time. So you can imagine what you can do with 10 tasks or 20 tasks when you have this capability. Also, every server on that machine has something between 64 gigabytes and 256 gigabytes of memory. So you can have really large models, and you can have multiple tasks working on these models. And then we have something else that is becoming during the later years is accelerators, or GPUs. GPUs are from the beginning normal graphics cards that some people notice that they have really much compute power. So some university researchers, they decided we can use this for computation instead. And now the big manufacturer of graphics cards, they actually develop dedicated graphics cards just for computation. And a large graphics card like an NVIDIA 2080 or something, they have over 3,000 cores. Small, not as big cores as you have in your normal computer, but smaller cores, but can do very specialized tasks, but there are a lot of them. That's why we have this excellent games today with really high resolution graphics and details. It's because you have so many cores working on the problem at the same time. So you have today multi-teraflop performance on your workstation hardware. And you have something like 200 to 400 gigaflops performance on your mobile hardware. And many of the computational analysis programs that have been using haven't been really caught up to these trends and scaled up, especially the ones that are running on your desktop. So the possibilities here is that you can actually do very many of these simulations in real time. So you saw that, Pierre, they showed a beam analysis, for example, and it was quite quick to show the results. So why not do this in the background all the time? so that when the user changes a parameter, the model is updated instantly. So you can directly see your changes of your model changes directly in the results. So also enable applications to continuously do calculations in the background. When, for example, when the user has changed the model, the program is intelligent enough to kind of, okay, I run speculative computation in the background, but just to kind of provide a result. And this technology can enable you to kind of directly manipulate the model using a direct manipulation concept. So when you move a node with your, for example, your iPad, the calculation is done automatically. You don't have the discrete calculation step anymore. And that kind of brings the explorability of the user interface. So the user can kind of explore what happens if I move this point. Is the model stable or not, or similar questions. So I will show you some examples here what we have done with the structural mechanics in the way of direct manipulation, explorable user interfaces. So as I said before, something that has been exploding the last years is multi-touch devices. You have that in your hand, you have it in your iPad, and many of these user interfaces on these devices are direct manipulation. So basically you take your finger and move something and it happens directly. And you get the feeling that when you move, you directly manipulate physical objects. And it's possible to take your existing mouse-based applications and adapt them for touch. And what we do in these programs is that when you model geometry, you also have this loop here all the time that simulates and visualizes results. Same thing when you add forces and boundary conditions, you simulate, if possible. I mean, the model has to be stable to be able to do simulations, but when you have a stable model, it simulates in the background. And you can also apply material properties. So you have this kind of continuous simulation all the time when you have done changes. So this is an example here of an application called ForcePad. I will show you that later here, where you move your force and it calculates the stresses directly and updates it in real time. So it gives you a completely new understanding of your models instead of having to wait for results all the time. So, as I said before, it gives you the possibility to interact directly with models. You can have kind of direct conceptual modeling. You can have a discussion with a client, discuss different designs, and immediately you get results on which you can convey to your colleagues or clients. You can explore your user interface. You can try out things, experiment, and also touch as you kind of you remove the need for input devices. You use your fingers instead. You also enable, you can use multi-user interactions. You can have a large surface table, for example, where you can interact with the models, multiple persons. They can see the same models at the same time and interact with them. And we did one test here in Vattenhallen for a long time ago, where we have a touch-based sensor on the whiteboard, where the users could actually touch the screen and interact with the model, multiple users at the same time. The only problem we had with smaller children, they couldn't reach the upper levels of the screen. So there are some problems with this model as well, but it's more geometrical with the size of children. Yeah, so this is a, let's skip this. So, so ForcePad is a two-dimensional finite element application. It's a standard-based Windows application. It supports direct manipulation. I skipped this, I think. We have done another application as well called Objective Frame, which is a three-dimensional application here, a frame application. So here you have a three-dimensional truss, and you can what's special with this application is there is no, you can interact directly, so you can put the force, and you can just kind of feel the structure here by moving the force around in 3D. And you can see the stresses in the structure as well in live. We also did an experiment here there is a special device called Leap Motion where you can sense your hands. So you put your Leap Motion sensor, which is, let's see here. This is the Leap Motion sensor here. So it can sense hands and the finger movement and translate them into a model. And we combine that into this interaction model so you can actually pinch and move your force using your fingers. So here we have some we integrate the Leap Motion. We simplify the user interface to kind of remove all the necessary steps to get to your model. And we're also investigating here how to make this more interactive to use multi-core as well. To have more complex models you can do in real time. We also did an application for the iPad called Sketchy Frame. And the idea was to investigate how to make finite element simulations on an iPad, and how much computational power you had, and see what you could do with it. So the idea was to create an interactive conceptual tool for education, communication, and discussion, perhaps also to kind of have a multi-user discussion tool. So imagine having your iPad and you can discuss your designs with your clients, and you can immediately kind of try out different ideas. It uses direct manipulation, so you can actually nodes and stuff that are moved directly by using the finger. There is no delay. It's a 2D frame truss analysis code. There is no simulation button. There's a continuous simulation cycle. It also detects mechanisms, so it only simulates your structure when the structure is stable. And if it's not stable, it displays the mechanism involved. And by default, it uses hinge beams, but you can add constraints to those beams to make them kind of fully they're connected in all the 3 degrees of freedom in each node. Yeah, so it eliminates the discrete calculation. So we're bridging the gap between modeling and visualization. Use of more modern architectures to enable directly interactable computational application. And you can also use this to teach and also to explore different models. So I had so this is a example of this application here. So you draw with your fingers. So basically you put the finger down and then you draw, and then it creates a node and a line between them. And then the nodes are added automatically. So you don't have to kind of create first the nodes and then the lines. It will automatically create the structure. Now you can just draw lines between the nodes, and it creates additional beams. And then we have to add some boundary conditions. Now you see we added a load, and now it directly did a calculation. And now we can drag the node around, or the load around, and it will automatically update the structure. And you can switch to see the forces in the structure as well here. So red is tension and blue is compression. Let's see. Yeah, so now we are adding rotational constraints here. So the nodes are now being squared, and then they're rotational constrained. So now we will visualize moment diagrams as well. So we have limited the calculation step, created, try to use new modern tools for finite element analysis as new devices for that, and also illustrated how direct manipulation can be something that can use to investigate and explore models in different ways. So I just wanted to show you live here as well some of the tools here. So this is the force pad application. So here you can draw, you draw with structure. You can also draw squares like this. There are three modes of operations. You have the structure sketch mode, you have a physics mode, and you have action mode. So in the physics mode, we add constraints. So we add boundary conditions here. So I lock it here. So these boundary conditions can simulate like a roller that can only roll in one direction. Then we can add some loads to it as well, like this. And then we go to the action mode here. Now you see here I have, it calculates the principal stresses in the structure. You can look at only the tension and also only the compression, or both. We can change the size of these if you want. We can make them only show not all of them at the same time. Increase the transparency. What the interesting here is I can change the direction of my force here directly, and I can see how this will affect the principal stresses in the structure. I can also move the force here around and see what happens when I move the force. I can show the stresses as well in real time. I can also see the deflection of my structure if I want, also if I move it around here. So this is a tool for exploring structure. There is another interesting thing as well with this. You can do optimization as well. So, so for example, if I want to optimize this structure for this force, I can just press here. It will create an optimized structure for this load case with certain criteria. So it's all something to look at. So that was force pad. I also show objective frame here. So this is objective frame. So it's a three-dimensional beam conceptual application here, similar to what Pierre had. This is three-dimensional. You can use the loads here as well and boundary conditions. But the interesting thing here, I can also do this direct manipulation here. So I can put the load here, and I can see what happens when I move the load around. I can put the load somewhere else in the middle here. and see how the structure behaves when I modify this. And I can also see here the forces in the structure when I move around here. So that was what I wanted to show here, to kind of, when you design your finite element applications or analysis tools in the future, when you get the product to develop, perhaps think a little bit about out of the box when it comes to the classical cycle here, to model geometry, do the calculation, and then do the visualization. Perhaps you can see if you can create something that is more interactive. Also, if you look at your own code that you have designed for this assignment here, there is this solver thread. This is kind of an embryo for running things in the background. So the reason we have this solver thread is to be able to run the simulation without interfering with the user interface. And you could fire off several of these threads, and they will execute in the background. So you could have something, say, when you move something, it will automatically run a simulation in the background. So threads are kind of the keys to do this in your calculation software. So, any questions on this? So I hope these two lectures here give you an idea on what kind of applications your project assignment here can lead to, or kind of what you can do with this knowledge from this course, and also gives you some ideas to kind of think a bit about out of the box when it comes to user interfaces and how you can make them more interactive. So otherwise, we have an exercise tomorrow. So thank you very much. Unless there is any questions, I will close now. Okay. Thank you. See you tomorrow then. Bye. Thank you.